Ladies and gentlemen, welcome to another episode of Heat Treat Radio. I'm your host, Doug Glenn, and I'm looking forward to talking today about something relatively interesting on vacuum furnaces, something called isolated heat furnaces. So we'll be getting to that shortly. Our speaker today will be Bryan Stern, who's the product development manager at Gasbarre Thermal Processing Systems. But before we get over to Bryan, I just wanted to mention that today, the sponsor of today's episode is in fact Gasbarre Thermal Processing Systems, and we wanted to thank them for their sponsorship. You can find out more about them on the web at www.gasbarre.com/thermal-processing-systems. We'd also like to thank the title sponsors for the upcoming Heat Treat Boot Camp, which is going to be held September 23 to 25 in Pittsburgh. But our title sponsors are Aerospace Testing and Pyrometry and also Control Concepts, Inc. And with that, let's jump into today's episode. Welcome, Bryan. Really nice to have you.
Already 4 years back. Thanks for having me on, Doug.
Time flies. All right, so we want to talk a bit about something that Gasbarre is calling isolated heat furnaces. In this case, these are vacuum furnaces. So let me ask you this: what is it? What's an isolated heat vacuum furnace, and why is it called isolated heat?
So I'll start off with, this isn't something that's Gasbarre specific. This is just a generic distinction and concept with furnaces. It's been around for a while, but the primary difference with an isolated heat furnace is that the heat chamber in that furnace stays at temperature in between processing throughout the process, and it's held under vacuum during that time as well.
Gotcha. Okay. And so we're going to talk primarily about vacuum furnaces, though. I know that's also possible in atmosphere, but we're going to be talking about the vacuum furnaces. The typical vacuum furnace today is the single chamber, I would say, right? Single chamber vacuum furnace. So maybe it's obvious already, but can you explain the difference? What are the differences between the isolated heat and a typical single chamber?
So the single chamber batch processing furnace, like you mentioned, is by far and away the most prevalent technology that's used. And the difference there is that everything in that process is going to happen in a sequential order. Everything from loading, evacuating the chamber, ramping everything, the chamber and the work up to temperature, holding it, doing whatever process you have, cooling it back down, backfilling it, and then unloading it. So it's all a sequential operation. You close the door, the work sits in the same place, and you run through the entire process. Whereas with the isolated heat, like I mentioned, it remains at temperature. So that's going to require three primary additional components in addition to your single chamber batch. It's going to require an extra chamber for evacuating, because you're going to have an antechamber or a way to load that work in after having pumped it down. So by default, you're going to have a second chamber. You're going to have some kind of dynamic sealing door between the two chambers that you can open once your evacuation chamber is pumped down, and you're going to have some means of moving the work between those two chambers. So the fundamental differences, but where it gets interesting is the impact that has on the rest of operation and efficiency.
Yeah. The single chambers dominated, pretty much dominated the market for a long time. How are those single chamber furnaces really affected the design of vacuum furnaces? And do these isolated heat furnaces, are there some significant design differences?
Yeah, it's one of those things that's kind of funny. Anyone who's familiar with single chamber batch furnaces will recognize there's a lot of challenges to doing vacuum processing that way. A really simple way to look at that is kind of looking at it like if you were trying to cook pizzas in an oven. That makes sense. You read the recipe on the back of the box, pop it in for 15 minutes once you've preheated the oven, pull it out. But if all of a sudden you had to start with the oven cold open the door, put the pizza in, and now you can't touch it until the whole thing goes through its process. You heat up the oven and then wait till it cools down at the end and pull it out. It wouldn't really be an ideal approach cooking pizzas. And that's the distinction with the vacuum portion of it specifically, because you have to pump it down. And consequently, in a lot of single chamber batch equipment, you have to wait to preheat the oven. So that adds a lot of time. And that sequential operation with that time where you have pump down on the front end and you have to go through a usually fairly lengthy ramping process to get up to temperature, that adds a lot of dead time in a process. And the answer to that, it makes vacuum processing more expensive. It's harder to scale. People know that. It's just a big inconvenience around vacuum processing in general. And the answer to that has typically been to increase workload sizes, because if you're going to have 45 minutes of dead time at the front, you'd rather distribute that cost over 1,000 parts instead of 100 parts. It just makes sense. So, and an effort to both increase the throughput that you can get through, so you're not waiting for a bunch of little batches, and you're not paying for all that dead time with a few parts. There's been a general trend to just increasing load sizes. And I say general, I am generalizing. It's not for everything. That sometimes it's necessary, but you get into some really massive single chamber batch furnaces, a lot of times larger than is necessary for the parts. And unfortunately, those load sizes are kind of detrimental to a lot of objectives of heat treating, where all of a sudden you have a much more difficult time maintaining uniformity for both process temperature and gas for the parts while you're heating up, while you're cooling down, and you're going to have just a much higher deviation between the temperature at the center of the load and the surface of the load, as well as process gas concentration. So that trend toward larger load sizes then necessary because of some of the inherent challenges with the single chamber batch method lead to some other challenges that you then have to overcome with larger load sizes. It takes longer to soak out. And quite often, something that I'm sure a lot of people will be familiar with, you end up leaving gaps in the work zone anyway, spaces between parts to allow gas circulation, to achieve quench rates, enable you to cool faster because you're not getting enough gas to the center of the load. So you have these massive loads, you've moved in a direction that's not really helping anything that you're trying to do. And that's kind of a bus that we've all been on.
Yeah. So I mean, you've got, let's say, interload or inside the load uniformity issues, obviously, and that's an interesting perspective on, because the process takes so long inside that one chamber. It tends to increase the size of the vacuum, or one of the ways to get around it is just increase the load size so that you're doing more at once.
Yeah.
So how about, I was thinking as you were talking, I was thinking also about if you've got how about the efficiency of the process, in the sense that if you've got a chamber that is designed just for isolated heat, you're just heating in that chamber. I would assume that chamber can be designed differently than a chamber where you're going to do preheat, perhaps convective preheat, high heat,
You're stealing my
cooling.
talking points, Doug.
Am I stealing it? Darn. Okay. Well, there you go.
No, absolutely. There's implications of trying to do everything in one space. I think the equipment design challenges really come from exactly what you're talking about. It's trying to heat and cool in the same space. And anyone who's been remotely involved in the production of single chamber batch equipment is familiar that you're doing a bunch of things that are kind of in tension with one another. Starting off with, if you're trying to cool in the same space, very often you're putting nozzle penetrations all through your insulation pack. So right away, you've shot your thermal efficiency in the foot, because you have direct radiation out of those nozzles. And people have tried, and with marginal success, to come up with kind of ways of sealing off those nozzles during the heating section, opening them during cooling. Some more static approaches, some active changes to the furnace. But the other issue that you have from that is you're hurting the cooling too, because you're restricting your gas flow. Uh, you're heating up the gas that you're trying to cool with by flowing it through this hot insulation pack. Um, your parts are sitting inside that heat cage, they're radiating to a hot surface. And as soon as you introduce multiple chambers and you can purpose design, move, and another thing that's worth pointing out too is that very often with a single chamber batch, because you have such a limited time to pump down and you're trying to decrease your cycle time as much as possible, the insulation is reduced just to help with vacuum levels. So it's, again, if you're holding that under vacuum and you can allow it to outgas and decay, now you can have a much thicker insulation pack. You're not putting penetrations through it. So it's helping your thermal efficiency in multiple ways. It's helping your cooling when you're struggling to get those cooling rates. You're going to do things like bump up gas pressure higher. So you'll be consuming more process gas. You'll put a bigger motor in it, which not only costs more upfront, it costs more to run. I think that's a fun fact about especially high horsepower single chamber batch equipment is that very often the current rating for the entire system can be driven by the gas blower alone. It's more than all of the rest of the power supply. So they're not cheap to run. And again, I'm not saying that you get away with half the size motor, but intuitively know you're requiring more than you would need if you place that load in a dedicated cooling space, no restrictions to gas flow, radiating to a water cooled jacket. So again, it's just a pretty intuitive observation just about the way we're currently approaching this.
Yeah, if you think about it, but people really have not, I don't think, have thought about it because it has not been the typical It hasn't been the typical way of doing it. It's almost all single chamber.
Yep, we're locked in there.
Yeah, yeah. But when you do start thinking about it, yeah, it makes a lot of sense that it would be your efficiencies would definitely improve, design efficiencies, operational efficiencies, all those things would improve because you've got dedicated chambers in a sense.
Yeah,
So
and another thing with that, just with regard to efficiency, something that we don't think about a whole lot is that you're sizing your power supply to overcome all those losses, the decreased insulation. And when you move to dedicated positions, in your position that you're ramping, that power supply can really be sized for that. And where it's building, it can be sized for that. And people have worked to overcome that with typical power supply sizing by doing things like adding multiple taps on the secondary side of the transformer to try to get a better power factor. But if you're dedicating stations within your equipment, then you can right size your power supply.
yeah. So that brings me to a question about. So we talked about the single chamber vacuum furnaces that have typically been used, and to my knowledge, there are not a lot of isolated heat furnaces or dedicated chamber vacuum furnaces out there. I know that one of the companies that you guys have acquired years ago, they made their name there. So so they are definitely out there. But have there been any developments in recent years that have led to let's say, the more popularity or the possibility of doing isolated heat furnaces, vacuum furnaces?
Yeah, it's a great question. It's something that I've done a lot of thinking about because I think we tend to have a mentality with technology that if it was really such a great idea, more people would be doing it.
Exactly.
So why aren't more people doing this? And
good question.
Yeah. So you could go ahead and take that one away, Doug.
Yeah, no, I'll let you answer, please.
I think we can actually learn a lot from looking at a couple other another industry specifically. The prevalence and immersion of some of the emissions regulations that are coming along is newer to our industry. I think we've been able to get away with doing things in a way that might be really inefficient for a while, but it's not new in some other industries. And a great example of that I love because I think it has so many great analogies to what we're looking at in vacuum heat treating specifically, but heat treating in general is, if you look at the history of the adoption of fuel injection in the automobile industry, I think I've always kind of assumed that fuel injection was adopted as soon as it came along. It was a better technology, but it was actually around since the 1920s and 30s. It was developed then, it was used in some military applications, and right away it was hailed as a better technology. It was more efficient, it was cleaner, but people just didn't want to change. That wasn't the direction that everyone was moving in. There were some manufacturers that tried. There were some mass-produced vehicles that had fuel injection as early as the early 1950s, but it still just wasn't taking off. And then in 1970, with the Clean Air Act that came along, that really was what pushed manufacturers specifically over the edge to start adapting it more, but it wasn't welcome. And some supporting technologies needed to be developed a bit better, especially with computers controlling those systems. As reliability increased for those throughout the 80s, there were some amendments to the Clean Air Act in 1970. Then it really started to hit the market and be adopted. And I think what finally sent it is that consumers started to experience the benefits, and they were aware of them before. And now we don't even think twice about it. It's the de facto standard. You're not going to go find, the car dealership in your area that has their specialty line of carbureted vehicles, and there are still places that they're used. But the advantages are so great because you've got dramatically improved fuel efficiency, much longer engine life. I mean, people say like cars just last way longer than they used to, and it's because this new technology that's been around for almost a century at that point, by the early 2000s, but it just had been sitting and people hadn't experienced the advantages of it. And one of the things that I love about that analogy is that it also demonstrates this isn't a complete switch. It's a gradual change for one, and there's still a place for the old technology. So I'm not by any means saying that, isolated heat furnaces are going to completely replace single chamber batch vacuums. But if you look at the kinds of places that carbureted engines are still used, you'll find them on a racetrack or in lawn equipment. So in these places where the upfront cost is really important, and then you're not getting enough operating time on it, that improved efficiency is going to pay off to pay that up front. You're just not using it enough. So that carries over well to some of the single chamber batch vacuums, because they will always be around, and they're definitely going to be more preferred in intermittent use applications, places where the runtime is not as long.
That's an interesting perspective. Have any of the technologies, have any technologies developed recently, like let's say transfer mechanisms or control systems or anything of that sort? Is there anything substantially new that had to come into place before you could get isolated heat furnaces, or have most of those technologies, similar to like the fuel injection, been around for a long time? It's just now we're starting to use them differently.
I think they've been around. I think like that analogous technology adoption, there's certainly going to be a refinement of some of those technologies. They need to be robust in order for this to work. There are some good solutions out there. There are some bad solutions out there. And I think the higher possibility of getting into a bad solution with a less mature product is one of those obstacles that people are facing. And when we're not changing, things don't change when forces are in equilibrium. So the fact that we're not changing as an industry to adopt some of this stuff just means that the forces motivating that change have not overcome the obstacles. And there's definitely some obstacles to it. And I'm sure we'll get into talking about those some, but we have that nudge from regulation that's happening. We're seeing that happen. We'll see and continue to see this type of product mature in those dynamic sealing mechanisms and transfer systems. And I think what's really going to send it is that there are a lot of benefits to address a lot of problems that we're all familiar with. It's just not the de facto standard, and there's ways that the industry is organized around the methods that we use currently. So a great example of that is you can kind of flip the pizza thing on its head. When you look at the back of the box of pizza, you've got a recipe that says preheat the oven and then pop it in for 15 minutes. If you couldn't do that anymore and you had to put the pizza in while the oven was cold and let it ramp up, now you've got to change the recipe. And that's the way that we're organized right now. We're organized with processes for material that's around starting cold. And it's actually a harder way to do things because the way that different equipment ramps is harder to control and quantify. So it's not necessarily a better recipe, but those are the recipes that we have. Another big impact is the vacuum level specifications, because in single chamber batch equipment, you're exposing it to atmosphere every cycle, and you've got to pump it down quickly. So even when you pump it to very low levels, vacuum levels, what's left is still often oxidizing constituents. Whereas if you can hold it at vacuum, even though it's not getting to the same ultra low pressures, if it's allowed to absorb from the surfaces and outgas from materials, even at a higher pressure, you can have a purer environment. And that's a really counterintuitive thing. It's not built into equipment specs because people associate the vacuum level with purity, and it's really more about dew point and the constituents of what's in the gas. You can have just as pure an environment, much higher pressure. And again, we're just not organized around that right now.
Yeah, and something you said earlier seems to me is, and you've kind of stated it, but let me state this and tell me if I'm accurate on it. You were talking about, because of the single chamber vacuum furnaces, we tend to increase the load sizes. So I'm assuming there's something to be said for on the isolated heat furnaces, where the load size could actually, or would tend to be, would make sense really for them to be a tad smaller or significantly smaller, and better uniformity, and therefore better uniformity within the load, both in the heat up and the quench. Is that an inherent, let's say, an inherent advantage of the isolated heat configuration?
So that's not specific to all isolated heat equipment. We have to get into discussing kind of the fact that you can't have continuous and non-continuous isolated heat systems. And it's an important distinction. The distinction just being you have your heat chamber, you're keeping it at temperature in a multi-chamber batch system, which is still a form of isolated heat equipment. You're going to be moving your work in and out the same direction. So you'll get a lot of the advantages that we've talked about. You're going to be able to have dedicated design for heating and cooling. You'll have your thermal efficiency. There's a couple things you're not going to get. You're not going to be able to increase the throughput. Whereas if you move to a continuous furnace where you're moving that work in and then you're moving it out to the other side, now to keep working with the pizza analogy, if you need more pizzas and it takes 15 minutes for a pizza, if you move that to 3 stations and it's 5 minutes a station, now you're getting a pizza every 5 minutes instead of every 15 minutes. If you're able to do that and produce loads faster, then you can decrease the load size, and then you're going to see all the benefits of decreasing that load size, the improved uniformity, faster soak times, better cooling. But you only get that if you go to continuous. That specific type of isolated heat equipment versus just any isolated heat equipment, you'll get much better thermal efficiencies doing that, because in the multi-chamber batch setup, you're not heating and cooling the furnace every time and throwing that energy away. But because you're loading and unloading on the same size, you're still going to leave that heat chamber unoccupied, sitting and holding at temperature, consuming energy in between loads. On a continuous furnace, you're not going to do that. It's never going to sit. You're never going to throw all that energy away. You're just minimal holding power required. So there is a distinction between the continuous and non-continuous isolated heat.
So today's episode is being sponsored by Gasbarre Thermal Processing Systems. And they design, manufacture, and service thermal processing equipment for various industries, including automotive, aerospace, energy, general industry, and industrial equipment. Their line includes continuous and batch atmosphere equipment, as well as multi-chamber vacuum furnace systems adaptable to many processes. Gasbarre is committed to providing value and design flexibility by understanding your unique needs. Taking a 360-degree approach from sales and engineering to design, manufacturing, and ongoing support, Gasbarre understands your process from all angles. Choose Gasbarre for reliable equipment designed to suit your needs. You can learn more about Gasbarre Thermal Processing Systems on the web at www.gasbarre.com/thermal-processing-systems. So we want to thank Gasbarre for their sponsorship. If the process required you to preheat, heat, then quench, what is it? Are you going to use transfer cars, or what are you doing there? How does that work?
If you have multiple heating levels, you can still control the heat, but often you'd introduce it at an intermediate temperature and then ramp it the rest of the way. So again, all of the advantages that you get. As far as quenching, typically with a two-chamber piece of equipment like that, your quench chamber is going to serve double duty as your evacuation chamber.
Okay.
So you'll be putting it into the quench chamber first, evacuating it, moving it in, bringing it back, and quenching it.
Gotcha. Okay, good. All right, so these systems sound good, sounds interesting, but I'm sure there's some challenges. So let me throw out some ideas here. I've been thinking about these, okay, is it all a positive story, or are there some drawbacks potentially? How about, I can hear some people saying, okay, these, especially the continuous version, these sound like great pieces of equipment. I can understand the efficiencies, but what about the complexity? Even the design complexity of these units. Is this an issue?
Yeah, it's definitely one that I face a lot on just the application side. It's a much more complicated process, especially when you get into continuous to fit the equipment to a process, because the process itself is going to impact each of those positions. Because now you care. If I go to sell you just an oven in your kitchen, the only thing I care about is, hey, Doug, it can go to this temperature. It can operate at this pressure. I don't care what you do with it. I don't care how much work you get through it. I just have these maximum parameters. But as soon as you move to talking about continuous, you're right away much more involved in throughput. For starters, that's going to drive often the number of positions to get the index rate you need for the load size. So now you care how long each step of the process takes, and you're trying to balance that among positions so that you're not letting anything sit longer than it needs to because you're jammed up over this particular soak time. So trying to get continuous equipment specifically sized for an application, I think, is more of a process than some people are expecting. And again, we're just not wired that way. So you can throw out a spec for a single chamber batch furnace, and you just throw, I need this operating temperature, I need this ultimate vacuum level, I need this uniformity, and we don't have to talk more about it. And then you come and you want to get into a piece of equipment like this, and it's like, we're going to have a couple conversations here. We're going to talk about some things that no one else is asking, and that can be a hurdle up front. Not a barrier, but a hurdle.
Yeah, not overcomable, but it also may limit flexibility, I assume, of the different processes you could run in that equipment too. I mean, I'm assuming, right? In a batch system, yeah, put it in there, do whatever you want. It's going to potentially take longer to get it done, but maybe in a isolated heat system, the heat chamber's only designed to do X, and you can't do X times 2, in it, maybe.
Yeah.
Does that make sense?
Yeah, it's not as much true just for a two-chamber, multi-chamber isolated heat batch style furnace, because you really have the same flexibility.
Right, but the continuous one
of get dedicated design on a continuous furnace, you still have the flexibility. It's just, if you're going to be doing that a lot, is it worth paying for something that can really be optimized one way if you're going to be using it in a flexible way? They have a lot of flexibility, I would argue, just as much as batch, It's just
Okay.
going to be a lot more expensive if
Yeah.
you're doing a process that doesn't require the way that that furnace was
Right.
built. So it's not that you locked yourself in. It's just if you're constantly changing processes, or you have much shorter processes, or the throughput isn't a benefit, then that's where a single chamber batch might be
Yeah.
a better solution.
Okay. And then the other objection that jumps to my mind is capital equipment outlay. Can you address that, compared to the single chamber?
Yeah, this is another one that's near and dear to my heart, because I think there's a lot of misconception here. I know I have had a lot of misconception because it's very application specific and hard to answer generally. Right off the bat, like we talked about, you're going to have another chamber. So if you're looking at a smaller system, it may not immediately be more cost effective. If you're looking at a continuous system that's replacing several furnaces, now you're not paying for that oversized power supply on each piece of equipment. You're not paying for a pumping system for each piece of equipment. You're just buying it for the one evacuation chamber. Maybe you have a backup, but now you're starting to distribute and be much more selective about your material cost. And there's definitely a break-even point in there. So it's really a question of whether or not the process improvements are enough of a benefit on the smaller size, but very quickly the upfront cost starts to be to lean in favor of the continuous, especially if you're looking at multiple pieces of equipment. But the bigger thing here, the thing that I feel more passionate about, is that we tend to get really hung up on the upfront cost. And I think that's something that can be very detrimental to just missing out on value for equipment, because it's very easy to just say, I'm going to have this amount of revenue and I'm going to pay this for equipment, and I'm not going to dive into maintenance and operating costs, because that's a difficult question to answer. It's a huge piece of the puzzle, but we often don't put in the legwork because the information is not readily available. And it takes a more sophisticated accounting approach to look at project value over the life of the equipment. I think intuitively we know that you could definitely pay more upfront for something that would improve efficiency or throughput or performance, that in the long run would pay off. And just going back to the car analogy, when was the last time you bought a car and you didn't pay any attention to the fuel economy on it? We know that, but it's hard to do that without a little bit more accounting elegance. So you have to look at the cash flow problem, do something like a net present value approach. And when you start looking at the operating cost savings, the efficiency improvements, and then a huge one that people miss is in these single chamber batch furnaces, we're heating it up and down, aggressive thermal shock and cycling. A lot of design goes into just trying to get components to last, because there's thermal ratcheting and things just wear out super quickly. These continuous systems that are just sitting at temperature, that goes away for the most. I mean, they're still consumable products, but the maintenance costs are dramatically improved. And you can talk to people who are using the systems, but again, that's not something a lot of people have experienced, and it's hard to quantify. So if you just look at the upfront cost, then it's really easy to miss out on. You're looking for a really aggressive payback because you're just hoping it's going to cover the operating and maintenance expenses that we haven't dived in and taken a look at, versus actually factoring those in and saying those overall for the project life are going to increase my value.
Yeah, that makes sense. All right, two final questions for you here. Kind of one question, but different angle. Are there any processes out there, or any companies out there, let's say types of companies out there, that really doesn't make sense to use a isolated heat type system, whether it be a double chamber or a continuous or whatever? And also, are you seeing from the activity that Gasbarre's been experiencing any industries that actually really should be looking at them?
So answering your first question with regards to the limitations, there's a couple situations where right out the gate, you're not going to want to be looking at isolated heat, probably.
Okay.
One of those is really large parts. If an individual part is actually going to take up your whole work zone, then you're not going to be able to decrease the load size and go to continuous and match the throughput. So very large batch applications, there's going to be an obstacle there. So large parts are one area that it's not going to shine. We're seeing really like 36, 36, 48 work zone is kind of the practical cutoff. So if you have parts that are larger than that, that's one time. Another is the ability to use work TCs to monitor internal temperatures of the parts. That's possible with continuous equipment. You can do a data pack and record temperatures, but it's certainly not as convenient. So when it comes to R&D, validating internal temperatures processes that require that, that's another hurdle and limitation of this type of system. Trying to think, the footprint's another one. Again, have that second chamber. So for just a batch style process, it's probably going to be larger in the space that it occupies, because you're not getting smaller in the work zone. So it's a question of, do you have the floor space, and do the other benefits of that system take up for the space it's going to take up?
Yeah. Okay. Those are good. Those are good caveats, right? How about industries that you're seeing that really should be adopting these things, either are or ought to be?
So I don't think it's super industry specific, but there are some processes that benefit. So just a couple would be anything with a really short cycle time, because the dead time of that is going to consume more of the process. So if you can eliminate that, if you only need to be at temperature for a little piece of time, then getting the rest of that dead time to be in parallel with the process to increase your throughput, that's a great candidate. But on the other hand, long processes are also a good candidate, because if you're holding at temperature for a long period of time, boosting that efficiency while you're holding the temperature and better matching a power supply to what you're doing. So short and long cycle times, any processes that require tight control, or it's beneficial to isolate them from the space. So sensoring can be a good candidate, carburizing, carbonitriding, where you can now actually have a dedicated space that maybe even operates at a higher vacuum level for whatever you're trying to do, where you're not worried about contaminating the parts with whatever process you're running, or you need a tight time control. So gas processes like that. Oil quenching's an obvious candidate, because you already have two chambers most of the time, and isolating it, maintaining it at temperature, and keeping it clean from any oil vapors. Oil quenching's a great example. Anything with expensive parts, you can minimize the risk by decreasing the load size. So instead of having this many 1,000-pound load that if something goes wrong, you've lost it, and especially applications where that can be a really expensive thing to have happen. If something goes wrong, you'd rather have it go wrong with much less material at risk.
Yeah.
So,
I would think traceability is also probably easier in one sense, with this isolated heat, in the sense that you're not having a huge batch in there. You're actually processing potentially smaller batches, and you're able to, isolate which batches were at what temperature or what kind of quench they went through. So be some advantage perhaps.
we had a very specific application for a customer that was concerned with a lot of small parts, traceability down to each part, and that's just they were looking at that system. Anytime you have a high volume of work, if you're looking at multiple single chamber batch furnaces to meet throughput, that's one of the biggest indicators. You really should probably be looking, and at least considering, these other systems. And anytime you have a lot of small parts in baskets, smaller parts than the work zone requires. If you see a large single chamber batch furnace with just stacked baskets of tiny parts, you'll probably have a lot of benefit from some of the things.
Yeah.
with a continuous.
I assume that if somebody is looking at currently looking at purchasing multiple single chamber furnaces, I assume you guys would have some sort of a calculator, let's say, to help them assess, okay, does it make sense financially and process wise to go with 6 batch furnaces or, one continuous? Is that a safe assumption?
Yeah, that's one of my favorite parts of the process, is to take a specific application, go through and break it down and put together that full project ROI, where you're actually starting to assemble, what are we looking at for maintenance costs? What is it going to cost to operate? And now you're starting to see at a project level, not just the upfront cost, which option is going to be best. And it is so application specific. It's neat to walk through that with a customer and see what comes out the other end, because at the end of the day, you want what the best solution is. It could be this, it could be that, but when you can actually put that picture together for a process and assist someone with picking the best equipment for what they need for their process, that's a fun piece.
Yeah. And just for the listeners' benefit, because we haven't done a lot of talking about your company, Gasbarre Thermal Process Systems, you guys can provide either. I mean, you can do the isolated heat systems, or if you do the calculations on your handy dandy spreadsheet and it turns out, you know what, no, you're better doing the standard single chamber, you guys can do those too. So it's not like you're going to push one over the other, whatever makes sense, right?
I see that as a huge advantage. You're not going to get the bias of we're trying to push you into this because this is what we're selling, but being able to actually wade through that decision and help pick the equipment that's best.
Well, Bryan, thanks very much. I appreciate your time. A lot of good info here. And yeah, hopefully we'll start seeing more of these isolated heat furnaces out there. So appreciate your time.
Cool. Thanks, Doug.
We hope you enjoyed today's interesting episode with Bryan Stern from Gasbarre Thermal Processing Systems. Give Heat Treat Radio a 5-star review or a like on Spotify, Apple Podcasts, SoundCloud, iHeartRadio, Podbean, or the website www.heattreattoday.com/radio. If you'd like to get in contact with Bryan, you can email him at bstern, that's BSTERN, at gasbarre.com. And you can find out more about Gasbarre Thermal Processing Systems at www.gasbarre.com/thermal-processing-systems. You can also reach out to me and I can put you in touch with Bryan or with Gasbarre, either one. Let us know if you want to hear a specific topic on the podcast, or if you'd like to sponsor a future episode. You can do that by emailing me. My email is doug@heattreattoday.com. Heat Treat Radio would like to thank Gasbarre Thermal Processing Systems for sponsoring this episode. And again, remember their website is gasbarre.com/thermal-processing-systems. Also, one last thing, consider attending, either you or someone in your company, attending Heat Treat Boot Camp this September 23 to 25 in Pittsburgh. This beginners event is intended to give new or up-and-coming individuals in your company a significant jump forward in their understanding of the North American heat treat market, including products, processes, markets, materials, and the manufacturers of heat treating equipment, components, and supplies. And we'd like to thank our 2 Heat Treat Bootcamp title sponsors, which is Aerospace Testing and Pyrometry and Control Concepts, Inc. This and every other episode of Heat Treat Radio is the sole property of Heat Treat Today and may not be reproduced in part or in whole without advance written permission from Heat Treat Today. I'm your host, Doug Glenn. Thanks for joining us.